Welcome back. In this video, we will be discussing one more math topic that many students struggle with: logarithms. Some of our measurements vary by large orders of magnitude, and scientists utilize logs and natural logs in order to make our data easy to understand. Some commonly seen examples of logarithms include earthquake intensity using the Richter scale, or sound intensity using the decibel scale. Many questions are brought up when we use logs in our general chemistry courses. Do I use log or natural log? What's the difference between the two? How do I do calculations with them? What tips and shortcuts should I learn? A logarithm is a number expressed as a base number raised to an exponent. Let's start with the example of 10 to the 5th. We now know that 10 to the 5th is actually 10 times 10 times 10 times 10 times 10. And if we plug this into our calculator, it will tell us that this value is equal to 100,000. The log is just rearranging this expression where the original number is called the base, the solution is our power, and the variable is the product of our power series. Now we can say log of base 10 of 100,000 is equal to 5. The word log tells us which function we are using. In chemistry, we will only use the bases of 10 and e. We will not add the base 10, as you see here. So if you see log, it is safe to assume that it's base 10. If you see ln, this is an indication that you are going to be using natural logs, which have a base of Euler's number, e. Where do I find these functions on a calculator? We are going to use the TI-30X2S calculator to show you an example. You will not be allowed to use a graphing calculator on most of your chemistry exams, so this is the typical calculator that you will use in your course. We also encourage you to use the same calculator for your homework in the example problems. Many manufacturers pair the log function and their inverse logs together. This is the reciprocal operation. Directly above the log button, you will see a 10 to the x. This is the inverse log function and can be accessed by hitting the second or the shift button. Similarly, the ln button has an e to the x, which is the inverse natural log. Let's try a few examples that you will see in a typical chemistry course. A hydrochloric acid sample has a concentration of 0.000357. What is the pH of this acidic solution? pH is defined as the negative log of the concentration of an acid. So we have to write a new equation. We have our pH is equal to the negative log. And if we know our concentration of our acid, we can plug that into our expression. When using our calculator to solve, we find that this pH is equal to 3.447. You will learn in your chemistry courses that a pH less than 7 indicates an acidic solution. We can also solve for the concentration of an acid given the pH. What is the concentration of a nitric acid solution if the pH is 1.39? Well, nitric acid has a formula of HNO3. So we know the pH. Now we must find its concentration. So we can use the same pH equation, but we're going to substitute slightly different this time. pH is equal to the negative log of our concentration of our HNO3. We were told that our pH is 1.39, so we're going to substitute that in for this value. The first thing I want to do is move the negative over to the other side. So how do I remove the log? This is where we're going to use our notation of 10 and raise it to a power. In this case here, our 10 and our log will cancel. And as you can see here, our concentration of HNO3 is going to be 10 raised to the negative 1.39. And that's all said and done, our concentration will be 0.041 for our HNO3. An example of natural logs can be seen when we are going to use the Arrhenius equation. That equation is going to be K is equal to A E raised to the negative EA over RT. You should note that the lowercase e is the anti-natural log e that is seen as e to the x on your calculator. In this equation, EA over RT is our x value. What if we want to solve for EA inside of our exponent? Just like using e to the x to get rid of the natural log, we can use the natural log to get rid of e. First, we need to isolate the e function by dividing both sides of the equation by a. We can cross out our a's on the right side. So when we have this, it will be k over a equals e to the negative EA over RT. Now we can take the natural log of both sides to get a much easier equation. The natural log here, and then if I take the natural log, I've got to make sure to capture both entities by parentheses. The natural log and e are going to cancel. And we'll be left with our exponent now being the only term on the right side. So what we will have is the natural log of k over a being equal to negative EA over RT. Finally, we multiply both sides of the equation by a negative RT to isolate our EA. Our two RTs and the negative will cancel on our right side. And we will finally have a resulting equation of EA equals negative RT. Then we have our natural log function of k over a. Logarithms are visually intimidating, But seeing that scientists have scales with many orders of magnitude, we can take very complex data and report it in a much simpler manner.